Okay, so today we want to discuss the radial equation for spherically symmetric system. Okay, so today's topic is we want to start with the radial equation. And in the beginning, we want to talk about some general considerations. Okay. So we want to keep our potential more or less arbitrary, but we shall, specialize to certain classes of potential. Okay, so let's write down the radial part of the Schrodinger equation. So there were two terms with derivatives of r, but those two terms of derivatives of r can be combined into one term, and that term is h bar squared over 2m r squared, and then there's a d by dr, and inside the bracket there's a r squared d by dr. Okay, so this is how we combine the two terms. And then there was an angular momentum eigenvalue dependent term, an L dependent term, and that was L times L plus 1 h bar squared divided by 2m r squared. Okay, this came from the fact that when we did the separation of variable, the constant that both equations was proportional to was simply the eigenvalue of the L squared operator. And then we have a potential energy term, which is V of r, and this is just a function of r, the modulus of the radial distance, of the radial vector. Okay, so this is a differential operator, all of this. And this, let me just make some room. And this thing acts on the radial wave function r, which is a function of r, and the quantum numbers are E, the energy eigenvalue, and L, because as we can see, this equation depends on L. So this is going to be equal to E times R EL of R. So this is the equation that we want to solve today, okay? Any questions?
No, sir.
Okay, so let's massage the equation and put it into a bit more manageable form. So suppose we introduce a new dependent variable, which we call u of ELR. This is not absolutely necessary, but these are the kind of algebraic gymnastics that you will find in the literature on differential equation. So now we express our original differential equation in terms of u. Then the equation becomes a little bit more familiar. So we have a term where we just have a second derivative of u. Okay? And so this will look like, we want it to look like the Schrodinger equation for a one-dimensional system. That's what we are aiming for. And then we have the angular momentum dependent term. And then we have V of r, and this is multiplied by u EL of r, and that's equal to E times u of EL of r. So this equation, the left-hand side, now looks like the Schrodinger equation. The whole equation looks like a Schrodinger equation for a one-dimensional system, right? But with this being the potential, an L-dependent potential, okay? So, recall that our full angular momentum, our full wave function is normalized in this way. We have psi star of x and with some, specified time. And this should give us 1, right? But we've also seen that the angular part, so this is the measure on a sphere, okay? And if I do y, L of m, and this depends on the natural variables on a sphere squared, that is equals to 1, okay? So if I do this, then for these to be consistent with this, then we must have that the radial part of the wave function must also give me an integral 1. So that means that, of course, the radial r, the radial variable r, goes from 0 to infinity, right? So it's not from minus infinity to plus infinity. And there's dr, and there's an r squared coming from this measure, right? Which is if we think how to think of R, we have a three-dimensional Cartesian space, but we can foliate this space by an infinite number of concentric spheres. And so what we have to do is that we have to integrate over one of these spheres, which say we take the radius of the sphere to be 1. And then we have to integrate over all the radii. And the radii goes from 0 to infinity. But of course, the area of the sphere depends on r squared. And that's why we have r squared coming into the dr integral. So there will be dr, and then there will be a part, the radial part of the wave function, which is, say, r el, and that'll be a function of r mod squared, and that should give us 1, right? And it's easy to show, just, it's obvious from the definition of u, because u is just small r times big R, is if you take the integration of 0 to infinity of dr, mod of u, e of L of r squared, this is 1, okay? So this is just, telling us that this is, we can think of this equation as a one-dimensional, Schrodinger equation living on the positive part of the real line, okay, from 0 to infinity. Okay, so let's introduce an effective potential. So to make this picture clearer, let's introduce V effective of R, and that's going to be the L-dependent term plus the potential energy. Now, so if I now write my equation, my Schrodinger equation looks like d squared u of EL of R, d of R squared. If I get rid of all the h bars and stuff, we don't want to get rid of the h bars, actually. Let me just write this as minus h bar squared by 2m. So this is the kinetic term. And then now we have a potential term, which is V effective of R. And this is, times U of EL of R equal to the energy EL of R. Okay? Is it clear what we have done here?
Yes, sir.
So we have just introduced an L-dependent effective potential. So, this effective potential, since it depends on L, it does something interesting. So, unless, this potential is extremely singular and negative, at small values of r, this is going to dominate, right? Because so for small values of r, this goes to positive infinity. So unless this goes to negative infinity in a way which is faster than, say, r squared, then this is going to dominate. Graphically, we can show this. So this is r, and this is, say, v effective of r, and it'll do something like this. It'll go down, and it'll do something like this. And so this could be v effective of r, but the real v of r, could do something like this. Okay. There'll be more divergence over here, but I'm just being very rough here. Okay. Now, the point is that this divergence, this positive blowing up of v effective at r goes to 0, this only happens if L is non-zero, right? If L is 0, then this term is not there. So this means that for particles with non-zero angular momentum, there is a repulsive angular momentum barrier towards r going to 0, and only L equals to 0 particles, that is particles in the L equals 0 state, are likely to be found near the origin, right? Do you see what I'm saying? Is that if the particle has, say, non-zero angular momentum, it's going to come in and it's going to see some repulsive potential, and if its energy is, say, below this, it'll just go and then it'll go away, right? But if it doesn't have any angular momentum, then of course it will not see this part, and then depending on what the rest of the potential is, what the v of r is, it can be attractive, it can be repulsive. The particle with L equals to 0 may or may not be found at the origin. Okay, is that clear?
So potential can't reach 0 at this situation, or can it?
You mean v of r?
Not
Yes,
be effective.
But it is 0 only when L is 0, right? If v of r is 0, suppose we are looking at, I say, a particle in a box, three-dimensional box. Then inside the box, v of r is 0, right? And outside the box, v of r is infinite. In that case,
unless both become 0, v effective will not be 0.
Yeah. So it'll become 0 if the angular momentum of the particle is 0. So it will be the spherically symmetric case in which it's 0. Okay.
Oh, okay.
So it's a very good question, I think, because what you're saying is that suppose that we have a particle in a box, and let me just draw a two-dimensional version of it. So I'm drawing a two-dimensional version of it, although it's three-dimensional that we are treating. So this is, say, the region near the origin where the angle, where the potential, say, is. non-zero. Okay, so this is a V, and V of R, and this is R. Okay, so that means that the wave function for this kind of system will only be non-zero at the origin if the angular momentum of that state is 0. Okay, so if the wave function looks something like this, that means that its L is 0. If L is 1, then it'll be something more complicated. Let me use a different color. It'll be something like maybe something like this. But the point is, it'll be 0 at the center. Okay, and and you can just this is basically some kind of something with the one node, but the node is at the center. If I take a cross section, it'll be, say, something like for the L equals to 1 case, the wave function will be something like this. Okay, I'm not saying it'll exactly be like this, but what I'm saying is that it's not going to have any. It's going to be 0 at the origin. Okay. Okay. Any questions? I mean, this is a kind of an intuitive idea. All right. So we figured out something about the nature of the system at the origin.